tired, you know?
How do you go to bed?
I don't know. 9?
Oh.
Ask me what time I woke up.
5.
3:45.
5:30. Your body just wake up?
That's my exercise time.
What?
My family leaves the house at 6. So that's why I'm tired. That's why I go to bed at 9.
Do you do that every day?
Yup.
We go at 3:45 every day.
Yup.
And go work out at 6.
No. We leave the house at 6. That's why I'm waking up at 3:45.
You leave the house at 6 to go to work or go work out?
to leave to go to work.
He works out. How far do you live from school?
It's about an hour. Because I have chores and dinners to cook and kids to put to bed, and it won't happen. And I'm tired at the end of the day.
How old are your kids?
My daughter's 5.
I could never do that. Oh, I'm just
So all right. Enough on our respective bedtimes. Today, I want to finish section 15.1. So we started this last week. I want to just kind of recap a couple of the important topics that we talked about before we move in to finish the rest of 15.1. So last time in 15.1, we talked about there being kind of two different forms that we could write our exponential function. We could write it as f of x equals a times b to the x, and then f of x equals a times e to the kx. Now, amongst all these exponential functions, we talked about how there was two types. There's growth and decay. And we can predict just by looking at the function, or the equation for the function, I should say, whether it's growth or decay. So if we're in the first form, f of x equals a times b to the x, and a is greater than 0, and b is greater than 1, that'd be growth. Or if a is less than 0, and b is between 0 and 1, that's also growth. So things like y equals 2 times 3 to the x, or y equals negative 2 times 1/3 to the x, would both be examples of growth, of exponential growth. For exponential decay, there's kind of two different ways to have that. If the a is positive, then the b needs to be between 0 and 1. Or if the a is negative, then the b has to be greater than 1. So for example, if you had y equals 2 times 1/3 to the x, or negative 2 times 3 to the x, those would both be examples of decay. And then if we're written in the other form, if a is positive and k is positive, that's growth. or if A is negative and K is negative, that's decay, or also growth, excuse me. So for example, like y equals e to the 3x is growth, or y equals negative 2 e to the negative 3x would also be considered growth. And then for decay, A is positive and K is negative, or when A is negative and K is positive would both be considered decays. So for example, y equals 2 e to the negative 3x is decay, as is y equals negative 2 e to the positive 3x. So these rules, and being able to use these rules to predict, like depending on the form, whether something is growth or decay, that feels like a good homework quiz-y type kind of basis for a question, whenever that might be happening in the not too distant future. The other thing we did on our last class was we talked about writing an exponential equation from a table of data. And we saw that that was pretty easy as long as we had one of our values in the table had the x-coordinate 0 in it. Because what we're trying to write is a y equals a times b to the x equation. So if we plug in for x and y, we have 1 equals a times b to the 0. And what's b to the 0 equal? 1, right? Any non-zero number to the 0 power is 1. So we just have now a is equal to 1. Great. So then I can use a second point along with the fact that now I know that a is 1. Let's write out. So we do it again. So 2 is equal to 1 times b to the 1. So I filled in the a for 1, and then the x for 1, and the y for 2. And here that we just get that b is equal to 2. So if we take those two together, we could write that y is equal to 1 times 2 to the x. Or really, I know that 1 times any number is just that number. So here I could just say 1 times 2 to the x is 2 to the x. Everybody's okay there? Okay. So what we didn't get to last time what is going on here? Stupid machine. I just want to make this thing bigger. I don't want that bigger with it. Oh my gosh. All right, so let's look at the new stuff then for 15.1, the stuff we haven't seen so far. So the first example that we're going to look at is kind of a story problem. So it says, given the population of a certain city in 1990 is 782,000 and change, And the population of the same city in 2000 is 895,000 and change. And assuming the population growth is exponential, in what year will the population reach 1 million people? So when I read a question like this sounds like a two-step question. So step one is going to be, I need to write an exponential equation. And step two is going to be to solve that equation. Does everybody feel okay there? So when I write my equation, I'm going to need, when I read this problem, I hear two variables or two quantities that are changing, right? One is time and the other is population. So I'm going to use T for time and then P for population. Everybody's okay there? Which one of those two should be the independent variable and which one should be the dependent variable? Excellent, yes. Population should depend on time. Time should be the independent variable. Almost always will time be an independent variable. Okay, so if we do that, these numbers look like ordered pairs to me, right? So if I take that, I'd have the points 1990, 782,248, and then 2,000, 895,193. But when I look at this, I look at my x-coordinates, neither one of them is 0, right? Which makes this kind of a hassle. So I'm going to do a little trick here to make my life easier. Instead of representing time as just like the year, I'm going to write T to be the years after 1990. If I do that, what does 1990 become? 0. Oh, I like where this is heading, Mr. Kulik. And what does 2000 become? 10. Very good. So do I need to do this, what I've just done? No. Why am I doing it? Makes my life way simpler. Yeah, remember that when we were given the 2 points, we had to write the exponential equation. You had to solve that system. Was a lot more algebra than if one of my x's is 0. So if I'm given a problem like this, I'm just going to define one of my x's to be like the starting value after whatever this, smaller of the x's is, so I can get away with not having to monkey around too bad. So since I have an x that's 0, that tells me that this value is just my a, right? So if I'm going to write my y equals a times b to the x equation, I can solve for b because I have an x and a y here. I have a value for a. And now I have everything I need to be able to solve for the b. Does everybody feel okay with what I've done so far? To solve for this b, what should we do first?
Divide the top number, 1990 population.
Yeah, divide both sides by 782,000 and change. Yep. And I could figure out what that is as a decimal, but I'm not going to bother with it. I'm just going to write it as a fraction, just hang on to it as a fraction. How am I going to get rid of that 10th power on the b? Well, not a square root, because it's not b squared. I want a 10th root. Yeah. So the way you write that is you put like a little 10 in the index. Now, note that because 10 is an even number, just like 2 is an even number when we do a square root, when we do the 10th root to both sides, it does generate a plus or minus. Still doing okay? Now, what do we know? Let's think for a minute, though. What do we know about our b in our exponential equation from last time? Yeah, excellent. So if you remember way back from last time, we said that b has to be greater than 0. So that just allows us to drop the minus off the plus or minus. So that's going to complete step 1 for us. Because now we have our value for b. And again, I could figure out the decimal, but I don't want to, because that's not the question that's being asked for us. Oops, we call this p, right? So that's the end of step 1. So what population are we asking to solve for in the problem? If we go back and read, 1 million. So I'm just going to put 1 million in for p and then solve my equation. So now we're starting step 2, right? Here's the hitch, though. We haven't got the algebraic tools yet to solve if the variable's in an exponent. So what are we going to do instead? We still have a tool that can do this problem for us. We're going to use our graphing calculator to do this. So to do this, I'm just going to type in the one side of my equation into y1 and the other side of my equation into y2. Now, to get a 10th root into your calculator, the way I can do this is I'm going to type in the number 10, and then I'm going to press math, and I'm going to do command 5, where it has like the xth root. And that's automatically going to take the 10 that I typed and make that the root. And then I'll type my fraction underneath it. And then we'll make that to the x. Everybody so far so good on getting this into our calculator? Now, before I hit graph, I want to think about my window, because I want to choose my own window here to do this. So let's think about it for a moment here. Remember, the x value is our time, So 1990 is 0. In 10 years, the population went up about 100,000. I'm guessing inside of another 10 years, it'll go up at least another 100,000, right? So I would think by 20 years, should be around where we're looking for. Does everybody kind of get the idea here? But I'm going to round up still. So I don't trust that like estimation I'm doing. I'm going to round up because I'd rather overestimate than underestimate because I just want to make sure I can see the intersection. So I'm going to make the X max 30. Everybody okay there? Now the lowest my population is ever going to be is that starting population of 782,000. But I'm not typing in all those stupid numbers. I'm just going to make it a round number as my Y min. I'll make that 750,000. Everybody okay with the reasoning there? Now, the population I'm looking for is 1 million. So the Y max needs to be a little bit bigger than 1 million. I'm going to do like 1.25. And that should be good. Should give me a nice clear picture there. I'm going to hit graph and take a look. So here's my exponential function that I wrote. Calculator's drawing that in. So notice that times 0, it's a little less than 750,000. There's the 1 million line coming in, so I'm interested in that point. So to find that intersection, I'll do second and trace. Pick the intersect command. Because I have just 2 curves in one intersection, I'll just press enter 3 times. And my answer is about 8.2. Or I'm sorry, 18.2. But remember that my value for t we said was years since 1990, right? Does this actually answer the question that we're being asked in the problem? Right? What is the question asking in the problem? In what year, right? So what year would we say? Okay, good. So we'd say during 2008. Everybody feel okay there? What if the question had instead asked, instead of what year, it said at the start of what year will the population reach 1 million? So here the big question would be, are we going to round? What's up, Jack?
No,
So the question here becomes, it asks now, at the start of what year? Should we be rounding that 18.2 up to 19 or down to 18? Well, you said up to 8. It was down to 18 or up to 19?
up to 19.
Up to 19 is correct. Because if we round down, the population would be less than 1 million at the start of 2008. Sometime during 2008, it'll turn to 1 million, and at the start of 2009 will be the first year the population exceeds 1 million. So everybody okay there? We have to be a little bit careful about what the question is asking to make sure that we've rounded things appropriately. Now, if I wanted to, we've written this equation to model the population for this city, right? So like if I plugged say 1,000 in for y1, that would tell me the population of this city in 1,000 years, right? So if I do that, I get like 5.6 times 10 to the 11th. It's like 100 trillion or something. 560 trillion people in a city. That make any sense to you? No. So what's going on here? Why is this model doing a bad job here? Yeah, there's like, it doesn't stop. The growth never slows down, right? Now, what do we expect a population to do once it starts to get too large? Or at least stop growing, right? Why would it stop growing? You've run out of resources, right? There's no more space. There's no more, food. Like disease becomes endemic, right? When your population density increases, rates of disease go up. All those things seek to slow down a population. So ideally speaking, we'd want something that grows fast in the beginning, and then the growth rate slows down and basically stops as it gets bigger and bigger and bigger, right? Can you guys think of any other things in real life that behave that way? Where it grows really fast at the start and then slows down? Great, so human development, right? When you're a baby, you grow really fast. You gain big percentages of your body weight really quickly. But by the time you get to maturity, that growth rate is basically stopped, right? Great. What are some other things that kind of grow that way? So if you're a business, sure, in the beginning, it's very easy to grow your business, but once the market becomes saturated, business growth tends to slow down quite steeply once everybody that needs your good or service has acquired your good or service. Absolutely. Some other examples that some other people in other classes came up with, like resource extraction. So like if you're drilling for oil, at the start of drilling for oil in the 1800s, it was very easy to get it out of the ground. There was a lot of it. It's easy to find and easy to get out. And as we've taken more and more out, you have to work harder and harder and harder to get that oil out of the ground, right? It's become scarcer. Like athletic development would be another example. Like if you're in the weight room lifting weights, you get strong real quick, and then it slows way down. You have to work really, really hard to continue to keep getting stronger and stronger and stronger. Those sick gains don't come quite as easy, to use the parlance of the times. So what we'd really want is to find, we see that this kind of behavior of grow real fast and the growth rate slows way down seems like something that happens a lot in the real world. We'd like a function that behaves that way that we can use to model situations like population or, business development or human performance or, these situations that behave this way. So there is a type of mathematical function that behaves this way. It's called a logistic function. So you can write a logistic function in either of these two ways. Notice in the denominator, you have that, what looks like an exponential function, right? Two different forms of exponentials. The denominator has those same two different forms of the exponential in it. Yes, go ahead, Colby. So we say that we have a logistic growth function when that b value is less than 1 or when the k value is greater than 0. It's going to be a growth, and it's a logistic decay if the b value is greater than 1 or the k value is negative. And kind of the cool thing about these logistic functions is that they have two horizontal asymptotes. One of them is always at y equals 0, and the other is always at y equals c. And the c here is just referencing that numerator. And what your logistic function looks like, well, at least a logistic growth, is kind of like an S curve, right? Kind of looks like a stretched out letter S there. So what's going to happen is it's going to grow very quickly in the beginning, and then that growth rate is going to kind of peter off at the end. So it stops growing nearly as fast and basically stops growing. This is exactly the kind of behavior that we'd expect from a population or from, a growing human or, a developing business or etc., right? So let's do a couple of just quick numeric examples. I did it again. So it says graph the following on your calculator. We're not going to do that quite yet. And then find the y-intercept and find the equation for the horizontal asymptotes. So we don't actually need our calculator to do this. So if I want to find the y-intercept, how do I find y-intercepts? We just talked about in the last chapter, right? That would be the vertical or the discontinuities. You make the x's 0, right? So we're just going to plug 0 in for all of our x's. So I have 10 over 1 plus 3 times 0.6 to the 0. What's 0.6 to the 0? 1. So really what we have is just 10 over 1 plus 3, or 4, which is just 2.5. So my y-intercept should be the point 0, comma 2.5. Everybody feel good there? NBD, right? So the horizontal asymptotes, we have 2 of them. One of them should be easy because it's the same every single time. It is y equals 0 it'll always be y equals 0. And the other is y equals c. So what's the c in this case? 10. So my other horizontal asymptote should be y equals 10. Everybody feel good there? Okay. Let's graph B. And well, actually, we'll graph A and just kind of see what's going on. So I'm just going to go to my calculator, y equals fraction command 10 over 1 plus 3 times 0.6 to the x. And then I'm going to reset my window now. I'm just going to go on my x's from -10 to 10. But the y's, I'm going to use my asymptotes as my guide. So my y min is going to be 0 for my first horizontal asymptote. My y max is going to be 10 for my other horizontal asymptote. And if I hit graph, there's my nice looking S curve there.
Can you back up on window part?
I use the asymptotes, 0 and 10. Yep. And if I look, what's the y-intercept look to be? It's happening, crossing somewhere between 2 and 3. That's that 2.5 that we observed earlier. Does everybody feel okay with how I got that into my calculator? Well, you probably typed your equation in wrong. Did you type in the equation for A or B? Okay. I have one more example. So here's a new population problem, right? But this time, instead of doing it with an exponential, we're going to do it with a logistic. So it says the population of a city can be modeled using the logistic growth function, P of t equals yada, 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 where P is the population in the city T years after 1950. Notice they did the same trick that we did, where they defined the time as like the number of years after a date. And then it asks at the beginning of what year will the city have 1 million people? This is no longer a two-step problem. Why is there not a step 1 here? They gave us the function already, right? We don't have to write our own equation. We have the equation that we're going to be solving. We just need to solve P of t equal to 1 million. Well, again, algebraically, we don't have the tools to solve this right now. So just like before, we're going to type it into our calculator. So I'm going to go ahead and type things into my calculator. Now I'm going to go ahead and choose a window. So I'm going to think hard about this. X is representing the years since 1950. So I'm going to assume the X min needs to be 0. Because at 0, I'm going to have like 1.5 million divided by 22-ish. Which is certainly going to be less than $1 million or 1 million people. The X max, though, I don't really have a good idea. I'm going to just put 100 here because 100 years seems like kind of a long time. Probably is good enough. Now for the Y min and Y max, I'm going to use my asymptotes. So Y equals 0. Is that for all logistic functions, that'll be my minimum. My Y max is going to be the other asymptote, which is the C value. But I'm not going to type in all those super specific numbers. I'm just going to do like 1.5 million. Everybody feel okay there? And then I'll hit graph. So here's my logistic function. There's my line for 1 million. I'm just looking for the intersection there. So second trace, intersect command, enter, enter, enter. And I get T is about 79.001. So that's giving me 79.001 years after 1950. But the question here asks, at the beginning of what year will the city have 1 million people? Well, how would I answer that?
The initial year plus the years that after 1950.
Okay, am I rounding 79 up or down? Up to
80.
80. And that's correct. Because if I rounded down, we'd be just a hair under 1 million people in 2029. Just agonizingly close, but not quite there. What do you guys think? Does that feel okay to you guys? That's, I think, as much as my voice is going to allow today. You can probably tell I'm getting a little bit hoarse. I was worse yesterday, but still, voice doesn't feel great today. I'd assigned 1 through 16 last time. You probably couldn't have done the story problems at that point. After today, I think you should be good with being able to do the last 8 or so problems in that 1 through 16. So there's not really a big addition to anything. It just, you can do more of what we assigned last time. Next time we'll worry about 5.2. And then, that'll be this week. So this 5.1 will be your problem set for Sunday. Will just be these 16 problems, which should be pretty doable. Well, we will, but it won't be till next week's part of next week's problem set, right? So I try not to give something on the day before or the last day of class for the week and make it due that Sunday. I tend not to want to do that unless I screwed something up, but I'm usually trying to be careful not to do that, to give you a chance to like look at some stuff and have questions or whatever. What do you guys think? Feel okay? Let's try to get some stuff done here. See if you can knock out part of this assignment. You got 40 minutes or so left in class, so try to be productive. But that's all I have for you guys. Yep. Yep. So here it's just asking us to write the exponential equation. So we're just given the 2 points here. X is 2, and k of x is like 16/9, and then x is 3, and k of x is 32/27. So we're just going to take our y equals a times b to the x equation and plug in our values for a and b. And that's going to kind of form a system. I'll refer to those two equations as a and b. So to solve this system, I'm just going to do elimination. So I'm going to take one equation and divide it by the other. My suggestion to you guys is always to take the equation that has the biggest power of b and make that the divisor. I should say the dividend of the division problem. So that's going to be 32/27 divided by 16/9. then a times b to the third divided by a times b to the second. So 32 over 27 divided by 16 over 9, I can just do in my calculator. I could do that by hand too, I suppose. So that gives me 2 over 243. That doesn't feel right. Not at all. I should be able to do it, man. All right. You're going to be uncooperative for me. 32 over 27 divided by 16 over 9. There we go. Now the a's are going to cancel themselves out, and then the b squared will reduce down to just that. So there's my b. Cool there, Mariana? So to get my a then, I'm going to pick one of the 2 points or one of the 2 equations. I'm going to pick the one whose b value or exponent on b is closer to 1. Typically makes life easier. Keeps the numbers smaller. So I'm going to just plug in for b, and now I can solve for a. 2/3 squared is 4/9. So if I multiply both sides by 9/4, I'm going to get 4 is equal to a. And if I put them together, I got that. Does that feel okay? You're welcome.